Okay, so we kind of left off with this linear regression stuff. We'll keep using a lot of those files today, just to kind of get some things out of the way. I just kind of, we've got those two current Connect and Excel assignments. I've kind of mentioned I dropped the lowest, so you know, really, if you don't do one of these and it's a 0, that'll be the one that gets dropped. But you know, got these sitting here, and then after today's class, you should be able to get through kind of all of the Connect and Excel, the 5th one, if you choose to do that one as well. So if we go back to where we left off, oh, I can't remember if I mentioned this either, but I'm starting to get my sections really mixed up towards the end here. So if I pointed this out last class, I apologize, but we have the final exam practice materials. So I'm going to update this formula sheet today. There was some things I'm going to add to it, but kind of you've got your 2 practice exams here. And we'll probably have a little bit more new material next Tuesday, but we'll probably already start doing some exam review next Tuesday and then Thursday, okay? So today's the real bulk of kind of the last new stuff. We'll get a little bit of new stuff, or at least kind of just more examples on Tuesday of linear regression. So we left off, we were kind of looking at Excel, we had that GPA data. We'll kind of play around with it again today, so we'll kind of give a review of that. But let's say we had kind of a different setup where I had this data set where I had individual income and then kind of the number of days the individual uses marijuana each month. Right? So I actually have this data set. We'll take a look at it in a second. But he's got about 5,000 observations. It came from a survey that tended to have younger individuals, and it was back in like I think it started in 1978 or 1979. So the income isn't adjusted for inflation. So the income numbers might look a little weird, but we at least have income measures and kind of the use of marijuana for all these individuals. So here's that regression output, and it's going to look slightly different than what I was showing you last class because this doesn't come from Excel. So when it comes to the exam, anytime I show you regression output, I'll use Excel output just because that's what we'll be the most familiar with. But we could see it come from other statistical programs as well. This one was called Stata. It really gives you the same information, but a couple things are different. So first of all, before we even get into it, the equation we're thinking about is that I've got this dependent variable, or this Y variable, which is income. And I think that it's some function of the number of days that someone uses marijuana each month, right? So I've got some intercept, and then I'll have some slope value associated with this marijuana. So remember last class, the general interpretation that we said we use for these slope coefficients is for every 1 unit increase in our X variable, that slope coefficient is the predicted change we expect in our Y variable. Okay? So if we're looking at this output, we've got our coefficient or our estimates for the slope and the intercept coefficient. So that is in column 1. It also is giving us our standard error, just as kind of a reminder. Oh, switch over to the dot cam here. Just kind of a reminder of what we're doing here. Every single time we look at a regression, zoom in just a little bit here, we're going to assume that slope coefficient is 0, because what we're trying to find is whether or not there is a relationship between that X and Y variable, or that slope isn't 0. We then say, okay, if we're calculating things like test statistics, we're just going to take the slope coefficient estimate that we see, subtract the assumed true value, but this is always 0, so we can almost like ignore that, right? We're always going to be using 0 here. In fact, we're not just using 0, we're always going to have this two-tailed test as well. We'll then divide by, just like we always do for a test statistic, a standard deviation of the statistic we're looking at. So what this is called with linear regression, we call this the standard error. So Excel gives us these two things. So to find the test statistic, all we have to do is divide that slope coefficient by our standard error. Then we have that test statistic. We could go look that up in a standard normal table, or sorry, not standard normal, a student t table, and find the p-value. But Excel does all that for us. So when I'm looking at this output, I've got my coefficients and my standard errors. How did I come up with these test statistics? Well, notice it's just the coefficient divided by the standard error here. This is almost, about negative 250. Standard error is about 50, so it should be a test statistic right around -5. Sure enough, it is, right? If you actually use the exact values, we get that -5.23. The p-value here is really close to 0. Oh, sorry. It's the end of the semester. I forget every single time that the first time I switch over, I have to hit that button. So, right, we've got this output here. We've got the coefficients and the standard errors. So how I came up with those test statistics, about negative 250 divided by about 50, it's gonna be around -5, right? A little bit more exact here because we use the exact values. It then gives you this p-value is 0, right? So remember what we're doing when we have a p-value that's pretty much close to 0. We're doing the same thing as we've been doing. We only reject that null if the p-value is less than alpha. So if I gave you different alpha values here, 0.1, 0.05, and 0.01, well, this p-value is going to be less than all of them. So I can reject the null at every single level. Or what am I rejecting? I'm rejecting that relationship between the x and y variable is 0. That the relationship between income and marijuana use, that there's no relationship. Right? I'm rejecting that there's no relationship. I found really strong evidence that actually supported the alternative, which in fact there is a relationship between these variables. Another way we would say this is we say that this coefficient estimate, I'm going to spell that wrong, is statistically significant. And what levels is it statistically significant at? Well, the p-value is less than 10. Sorry, it's less than the alpha at the 10% level, less than alpha at 5%, and less than alpha for the 1% level. So it's statistically significant at all levels, right? 10, 5, and 1%. Okay. Another thing that you might see in this different programs output is instead of the intercept, another term sometimes used for this A value or the intercept is the constant, right? No matter what marijuana usage is, right? A is the constant in every single kind of prediction of income that we're making. Yeah.
If we were going to do the test statistic not in Excel, what's going on in the denominator again?
It's just this coefficient divided by our standard error. Yep. So you can almost think about if I left these out, you're just dividing that coefficient by the standard error for each variable. Well, we only have one variable here. Eventually today we'll see what happens when we have multiple variables. Okay. All right. So I think, right, how do we interpret these coefficients? So this slide will kind of have laid out what I'm about to say, but we said that in general, the interpretation is a 1 unit increase in our x variable causes the predicted y value to change by whatever that slope coefficient is. So a 1 unit change here is if an individual uses marijuana 1 more day a month, we would expect the predicted income for that individual to fall by $253. So that's the interpretation of our slope coefficient. For the intercept or the constant, we said the interpretation of that is always if the x variable is equal to 0, the intercept or the constant is the predicted value of y. So in this case, if somebody used marijuana 0 days a month, well, 0 times any slope coefficient is 0. So when that x variable is equal to 0, when they use marijuana 0 days a month, the predicted income would be $32,450 about. So I'm just trying to, the interpretation, like the template for it doesn't change. It's just you have to change it to the context of whatever example we're looking at. So we'll just keep getting more examples and doing more interpretation. I think this will become a little bit more, innate, and you don't have to think about it quite as much. So I've kind of got those interpretations here on the slide that I just said, right? So I've got the 1 unit change or 1 more day a month causes the income to go down by $253, and then I have that intercept interpretation as well. Okay? So anytime in a homework or on the exam, when you see this interpret this coefficient, this is what you're doing, right? You're not saying it is 253. No, here, give me the full interpretation, okay? So I kind of already brought this up. We have these tests we can do for statistical significance. We said, I think I said last class, we're always going to use the two-tailed test, and we're always going to use that assumed true value of 0. I've already mentioned this today, but this is just kind of a reminder of that. So let's say we ran another regression where I want to try to predict birth weights based on the mother's smoking behavior while pregnant, right? So this is going to be a slightly different than the example that we just looked at or the one from last class, in that we have what we call a binary, a dummy, or an indicator variable. All three of those words kind of mean the same thing. I'll probably more often than not call it an indicator variable, which is just a 1 if the mother smoked while pregnant and 0 if she didn't. So I run this regression. I've got my Y, my dependent variable is birth weight, my X or my independent variable is whether or not the mother smoked while pregnant. How would I find the test statistic for this smoking variable? All I have to do, take that coefficient of negative 213, divide it by the standard error of about 49, and I'll end up getting that negative 4.36 test statistic. In addition to this, how would I interpret my slope coefficient on smoking, mother smoking while pregnant, and how would I interpret the intercept? So for the smoking variable, right, we follow that template. A 1 unit change in the X variable causes the Y variable to change, go up or down by whatever that coefficient is. Well, here, what's a 1 unit increase? The smoking doesn't measure like the number of cigarettes that the mother smoked. It's simply a 1 or a 0. So a 1 unit change with an indicator variable is going from 0 to 1, going from not smoking while pregnant to smoking while pregnant, right? So if a mother smokes while pregnant relative to not smoking while pregnant, the predicted change in birth weight would be, it would go down by 213, and I believe I should have had this out here, but it's measured in, measured in grams, right? So it goes down by 213 grams. And then how would I interpret the intercept? Well, if the interpretation of the intercept is if the X variable is 0, the intercept is the predicted value of our Y variable. So here, if the mother doesn't smoke while pregnant, right, that will be a 0, then the expected birth weight of the kid is 3,427 grams. So once again, just getting more interpretation. Every time I show you this, I don't have the question on the screen, I'll go through how we would interpret those different variables. Okay? The coefficients associated with those different variables. Okay. All right, so we kind of went through this last class talking about minimizing the sum of the squared errors. I kind of jumped the gun a little bit, so we won't have to go over this again. But we said if we did minimize the sum of those squared errors, right, what we're really trying to do is get this line of best fit such that the errors we're making with our predictions, right, the line kind of represents our predicted values, that we're minimizing those errors, right? We're minimizing the total kind of sum of those errors. Now we're squaring them because we said we don't care which direction we make the error in. We also really want to over penalize egregious errors. But the idea is we're trying to minimize the errors that we're making with our predictions. So we have, this equation that we can, take derivatives of, and then, 2 equations, 2 unknowns, and we said we'd get these formulas. I said, I'm not going to make you use these by hand, right? But I did want to show you today that you could do this in Excel, and they used to actually have to do this by hand. So you can kind of see how much of a pain it's going to be to do in Excel not using the built-in tool, and imagine what it used to be like before we had computers. So I've got this linear regression height and weight completed file under that linear regression folder on the in-class data tab on Canvas. That was a mouthful. So all I did here was I'm first going to try to calculate what that slope coefficient is by finding this numerator. So take the observation's X value minus the average X, and multiply that by that observation's Y value minus the average Y. So I found the average height, right, or the mean height. That's pretty easy to do. I then found the average or the mean of my Y variable, which is weight. So the equation I'm kind of thinking about here is I'm trying to predict weight using height. Right? That's this kind of regression equation I can think about that I'm going to try to run here. So then what I did is for every observation, I took their height, right, their X value, subtracted the average X value. I then took that observation's Y value for weight, subtracted the average Y value, average weight. I then multiplied those 2 things together. I did that for every single observation. I then added them all up. Right? That's what's going to give me my numerator. Right? That's all the numerator is saying. Take the difference for every observation, look at their X value, subtract the mean X, multiply that by the Y value minus the average Y, and then add them all up for every observation. I'm then going to do this denominator. So the denominator says, take that difference between the X value and the average X for every observation and square it. Once you've squared that for every observation, add them all up, and that's your denominator. So I now have my numerator and my denominator. It's simply a matter of dividing that numerator by the denominator, and I get the coefficient estimate or a slope coefficient estimate of 4.713. So I can do all this work any single time I want to do a regression, or if I've got that data analysis tool, it's basically going to do all the work for me. So I go down to my regression, right? Y variable is weight, Control Shift or Command Shift on a Mac and hit the down arrow. And then I'm going to select my X variable. And here's a little trick, if I can remember which one it is. I think this is my height column. Instead of scrolling all the way back up, Control Shift and hit the up arrow, just going to select that entire column for me. So I now have height and weight in there as my X and Y variables. I'm selecting the labels. And what I'll notice here is 4.71318, or whatever it was, is the exact same thing that I have over here, right? So it saves me a lot of time. I don't have to do all this work behind the scenes. I don't have to worry about, oops, I was going to try to show you this cell. I don't have to worry about freezing things, right? So it just makes my life a little bit easier to use that built-in tool in the data analysis. You can imagine you used to have to do all these calculations by hand. Like I don't even understand how people have the motivation. But you know, with a computer, with Excel, this becomes a lot easier. Okay? All right, so we can use these forms of the equation, or basically we just can allow Excel to do it for us and spit back out at us the results. Right? So we can kind of ignore some of this because this is just me setting things up in Excel. Where do I want to go with this here? Oh, the Excel formula. So the formula really was just going to data, using that data analysis option, right? That was basically going to do that entire formula for us behind the scenes. We had to select each variable. Yeah, okay. So I'm going to jump around a bit here in the slides, but what if we had something like this, right? So up to this point, I've only looked at the relationship between this Y variable and one X variable. Well, you can add several other variables there on the right-hand side, or we can add more independent variables. And that makes sense because if we're trying to predict weight based off of height, well, there's a lot of other factors that probably are better at predicting weight. So we probably want to throw those in and try to come up with a really good prediction of what someone's weight is, not just based off their height, but you know, their height, you know, their diet, list a million different things, their age. So we can include several different X variables. Now, typically the way that we'll see this kind of written, so instead of using A and B now, I just kind of do that so we can compare more to probably what you've seen in a math class. Once we have multiple variables in a regression, more often than not, you'll see this written as using the coefficients are written as beta. Beta 0 is the intercept. Beta 1 is associated with the first X variable you're looking at. Beta 2, the second X variable, so on and so forth. Right? And you can really include, you know, a very large number of X or independent variables here. Okay? So I'd say return to the crime equation. I think I didn't use this example, but imagine if we had an equation that looked like this, right? So I'm trying to predict crime rates based off of the unemployment rate in the area and police expenditures, right? So this police variable is how much money that city or that or state, depends on what kind of data we have, is spending on their police force. And then the unemployment rate in the state might also impact crime levels. Okay? So the interpretation now becomes, oops, well, I think I'll hold off on the interpretation. So this is the idea of what we're doing. We would actually find these coefficients the exact same way, right? I could write out what's my error. My error is the actual Y minus the predicted Y. And I'm trying to minimize the sum of those errors squared. How do I get my predictions for the Y value? Well, it's just all these slope coefficients multiplied by the values for X. Well, I now have, instead of two things that I'm trying to figure out what the best values for, I've got N number of things. So I take a derivative of this equation in respect to each coefficient, right? And then I set them all equal to 0. Now I have N equations, N unknowns, and I can, you know, solve that. It's just going to take me a lot more time. So I think I've got, you know, I'm not going to kind of walk through and show you how we actually go through, you know, solving those N equations, N unknowns. But if you're interested, there's kind of a guy at UC Davis that kind of has a pretty good, what I think is a really good explanation, or, you know, not explanation, but walks through the steps mathematically pretty well. But for us, all we need to know is we can do this in Excel really easily. It'll do all that kind of computation behind the scenes for us. Okay? So the interpretations of these coefficients are going to be exactly the same, right? So it's still the expected or predicted change in our y variable from a 1 unit change in our x variable. That's how we interpret the coefficient. The only thing that we add now is holding everything else constant. And that might not seem like a lot, but I'll kind of point out as we work through these examples just how powerful being able to add this last statement is. And then the intercept interpretation is going to be a little bit different. Now, just instead of the one x variable being equal to 0, now we could think about it as, I'll go back to the crime one. Now it would be if both of or all of the x variables were equal to 0, the intercept is the predicted value of our y value. So it's really the same thing. It's just now we don't have to say if one x variable is equal to 0. We say if all the x variables were equal to 0. So not a whole lot that's wildly different there about the interpretation. But, oops. Oh, what do I want to do here? I think I'll stop. I'll go to the Excel here. So we're going to stop on this r squared. So we've got our new interpretation. We said it's a little bit different. We can hold everything constant. Right? So I'm going to go to this GPA data kind of in class. Right? We're going to start thinking about what we'll eventually call kind of this omitted variable bias. So maybe I want to predict GPAs using SAT scores. So this is what we did last class, right? And I'll upload this file after class today when we do a little bit more work today with some regressions. So if we ran this simple linear regression with just one x variable, we came up with this coefficient, right? But it's likely that a lot more things other than the SAT score are impacting GPAs. Okay? So one thing we might think about is, and I'm just going to right click here and insert this. So I'll show you why later. I'm going to move this athlete variable over here. Okay? Now the reason why I'm doing this is because when we start to add in multiple x variables, the way that Excel works is they need to be in columns that are next to each other. They can't be separated by other variables that we're not using. So here's the idea. SAT scores impact GPAs, but so does maybe being a student athlete. So you might have the question of, does being a student athlete positively or negatively impact that student's college GPA? Because it teaches you time management and potentially, that has a positive impact, but it also requires time, right? So it might, have as much time to study potentially. So we might be interested in this, right? So we'll go to our data analysis tab or option, hit regression, and I'm going to select college GPA to be my y variable. And then my x variable, I just want to see what's the impact of being a student athlete. Okay? So I'll go there. I selected my labels. I'm going to hit OK. I'll blow this up so we can see it a little bit better. So we've got our coefficient estimates. So the interpretation here would be that if the x variable changes by 1 unit, well here athlete is just a 1 if they're a student athlete, 0 if not. So being a kind of student athlete in college relative to not, would you predict that that person's GPA falls by what, 0.28, which is a pretty sizable decrease in GPA. And then we can say that it's very significant, right? E to the negative 9, remember, means move that decimal point 9 places to the left. So this is pretty much 0. The interpretation of the intercept, if the x variable is equal to 0, so the person isn't a student athlete, the expected GPA here will be about 2.66. Well, we haven't, just being a student athlete, there's a lot of other things that are going to impact your GPA. So we'll go back to the raw data here. And I'm just going to think of one thing that might matter, right? So one thing that might influence college GPAs that's also correlated with being a student athlete. So if being a student athlete, if student athletes are on average of higher intellectual ability or on average of lower intellectual ability, then that athlete variable is not capturing purely the effects of being a student athlete, but it's also capturing the effects of being higher or lower on average in intellectual ability. And if student athletes tend to be more likely to come from higher income families, well, then it's capturing that effect as well. So every variable we leave out of our regression equation impacts the coefficients on the variables we included, if those variables we left out are correlated with the x variable and the y variable we're looking at. Well, SAT scores, I have to imagine there's going to be some difference in student athletes versus not, right? first of all, if we're looking at D1 programs, I mean, just the revenue incentives for men's basketball and football to maybe be a little bit more lax on your academic standards, there's a really strong incentive there. So we probably think that exists. So what I'll do is go back to my data analysis. Now I already have that college GPA selected as my Y variable, but now for my X variable, I'm gonna just take athlete and SAT scores, right? Hold Control Shift, hit the down arrow. So I'm now selecting two variables, and I'll have two variables on my right-hand side, or as my kind of independent variables. Another way to think about this is the variables on the right-hand side are your predictor variables. They're trying to help you predict what that Y variable value is gonna be. So we hit OK, and we go ahead and look at this. All right. So just to kind of compare to our first regression, it looked like being an athlete was a bad thing, right? Hurt your GPAs. If we just include this control for SAT, the interpretation on our athlete coefficient now becomes a 1 unit increase, so being a student athlete relative to not, would change your predicted GPA by only about, it would go down by about 0.05, holding everything else constant. So here, holding the SAT score constant. So the thought experiment starts to become, when you can hold other things constant, it's almost as if you're able to take two people with the same SAT score, but one of them is a student athlete, you would predict that that person's GPA is 0.05 lower. Now, we only have one thing to control for, but you can imagine if we start to throw more things in here, and we'll see this in a second, we can make really powerful statements. And notice, so this went negative. So we could still say, yeah, being a student athlete looks like it's a bad thing, but now look at the p-value. At a p-value of 0.25, we actually can't reject the null hypothesis at any of our conventional levels, right? An alpha of 0.1, 0.05, or 0.01, we're not less than any of those. So I can't reject the null hypothesis, which is that that slope coefficient is equal to 0. So not only did the size of our estimate go down, but its significance completely went away compared to when we just ran that simple linear regression. And that's because SAT scores are different between athletes and student athletes, and SAT scores are really good predictors of college GPA as well. Right? So this kind of highlights that if you're omitting important variables on that right-hand side, you're omitting important variables that would help you predict your Y value, then you're going to have coefficient estimates that really don't make a lot of sense because they're capturing the effects of all those variables you left out. So what we might want to do is like what sometimes people refer to as throwing the kitchen sink at this, right? Well, I've got a lot of other data. Why don't I just use all of this? Now, we're going to kind of punt on using this SAT squared. I might show you something with that next week just to pique curiosity. But for now, I'm just going to move it over here because I'm not going to use it in this regression. And I need all of the variables that I am going to include to be right next to each other. Okay? So I move those around. I go back to my data analysis option or tool, I guess. I've still got my Y variable as college GPA, but now my X variables, I'm going to include everything, right? So, I've got racial identifiers, gender, total credit hours taken, high school size, their rank in high school, all these things, right? Control Shift, hit the down arrow, I'm going to select all of them. Now when I look at this regression output, I've got a ton of control or a ton of right-hand side variables there, right? I could start to do interpretation for all of them. I'll probably pick a few here. For instance, now notice the athlete variable. So 1 unit increase, being a student athlete relative to not, now predicts that GPAs would be 0.17 higher, holding all this other stuff constant. So two individuals with the same SAT score, they had the same high school rank, they got the same score on this verbal math test that we have data on. They were either both female or both male. They were either both of the same race. They both took the same number of credit hours. They both came from a high school that has the same size. But one of them is a student athlete. We would expect that person to have about 0.17 points higher of a college GPA. So I mean, that's a much more powerful statement, right? Because I'm comparing otherwise like two pretty identical people, but just one little thing is different about them. You would expect that student athlete to have a 0.17 higher GPA. And the p-value is pretty much 0, so we can say statistically that this is a significant effect at all levels. Right? Now, So just to recap, we started out thinking being a student athlete is bad. We controlled for just one other thing that we know is really important on predicting GPAs, which is the SAT score, and it looks like it's not as bad. Maybe it doesn't even have an effect. To where if we can control for a variety of factors that influence GPAs, now it looks like maybe being a student athlete is a good thing. Any questions on, I know I kind of went through some of that quick, especially, I'm running this regression, but it's really the same process every time, just selecting, a few more variables. Okay. Any questions before we keep moving here? All right. So I'll talk about causation and correlation here in just a second, but that's basically what we just got at, right? We might look at this original regression and say, oh, that's not what we'll say. Here we go. We might say, being a student athlete looks like it's a bad thing. Being a student athlete is causing kids to have worse college GPAs. But then we say, well, if we can control for all these other factors, it's not necessarily that being a student athlete was causing GPAs to be lower. It was that being a student athlete was correlated with lower GPAs because being a student athlete was also correlated with a lot of these other variables we didn't include in the regression. Right? It wasn't a causal relationship, it was just correlated with seeing that increase or decrease in GPAs. So if we go back to the slides here, I've got this slide on R squared. So what is R squared? Well, here, I'll kind of give you a rough overview and then tell you what you should know about R squared just for the sake of this class. So R squared represents the percent of the variation in that Y variable that you are able to explain with your X variables. Right? So obviously, the highest that it can be is 100%. In an ideal world, we'd have data on every single thing, say that influences college GPAs. We'd then run the regression and we'd get an R squared of 100, right? Our X variables explain 100% of college GPAs. Now, do we ever get R squareds of 100? No, because right? Think about it. For everything, you'd have to have every single factor that played a role in the GPA that someone gets. It's probably impossible to have that much data, but we can get close on some things, right? We can at least control for the most important factors, and we'll take a look at the R squareds from those regressions in a second. So what we're really thinking about, how do we come up with this R squared? Well, we look at the difference between the actual Y and the average Y. So this involves no predictions. This is looking at that Y variable. So I might look at GPAs. This is kind of like measuring the variance, right? It's the deviation of every observation from the average Y value squared to overpenalize extreme variations. And then we add them all up. So this is like how much variation there exists in that Y variable or in GPA scores. We then take a look at, okay, if I look at my predicted Y values and how much they differ from the average Y, square them, add those up. This is essentially capturing how much of the variation or how much variation there is from the average Y from our predictions. Well, we know our predictions are going to be a little bit off of the actual Y values, right? We have this error term. So if I take a ratio of these two things, it's like how much variation exists in my predictions relative to how much variation there exists in the actual Y values, which we know there will be more variation because the actual Y values incorporate that error term. So that's what we're essentially doing with that R squared. But Excel is going to do it for us, do all this computation for us. You can imagine I could come up with this in Excel, and I'll kind of give you an idea about how we come up with those predicted Y values here in a second. Let's see where we're at in time. So what you need to think about the R squared is it's just telling you how much of the variation in the Y variable you're explaining with the variables you included on the right-hand side, or your X variables. So if we take a look at those regressions we just ran, so we'll go back to that GPA data. The very first one, where I only included as the person a student athlete, my R squared, and don't worry about the adjusted or multiple, that we're going to kind of punt on those issues. We're just going to focus on the interpretation of R squared. I explained, and here they don't show me as a percent, they're showing it to me, Excel puts this out as like a proportion, right? But the proportion of the variation I'm explaining in GPAs is what, 0.008 or 0.8% of the variation? That's hardly anything at all, right? I'm barely, like, being a student athlete apparently is just a very small piece of what your college GPA is going to be. If I include just the SAT score, as well as that being an athlete, now my R squared is as high as almost 17%, right? The proportion of the variation I'm explaining in GPAs with just these two variables went from 0.008 to 0.167. So here, this is an indicator that like SAT scores are explaining, roughly 15 to 16% of the variation that we see in GPAs. Yeah.
So is it kind of like the higher R square is,
Mm-hmm.
the more accurate?
The more accurate your predictions are. You're capturing more of the variation that exists, or you're, think about it this way. Yeah, when we thought about what that R squared is, if I'm getting better predictions, this starts to look closer to this, right? My predicted Y's will start looking closer to my actual Y's, and so that ratio will get closer to 1 or 100%. Yep, it's a good way to think about it. Well, then what happens if I throw the kitchen sink at this, right? And I included a ton of different variables on the right-hand side there. Now I've got an R squared as high as almost 30%, right? I'm explaining about 30% of the variation that exists in GPAs with these variables. Now, seems like I threw a lot at this. I have a lot of control here. Notice there's still 70% of the variation I can't explain. So I can make predictions using these estimates, and some of them are statistically significant. But I need to be cautious, right? Because I'm still missing 70% of the puzzle, right? I still don't know 70% of what's driving GPAs. So yeah, that's the idea of the R. So we like to see a high R squared, but just because it's not high doesn't mean that we aren't finding, like for instance, we are finding evidence that this is somehow correlated with GPA being a student athlete, but because there was so much left that we couldn't explain, we don't know what happens as we add more control variables, what's going to happen to that coefficient. We can kind of already see when we added just these, well, now we get a very different estimate, right? So we need to be cautious when R squared is low. And how low is low? There's no benchmark. I mean, typically you'd like to see R squareds at 70 or 80% because, you're just thinking, they're not missing as much there. Here, we're still missing quite a bit. So, but that's okay. It's a good example. So, let's think about this idea of correlation and causation. So let's say I run this regression, go back to that idea of predicting crimes. How would I kind of think about it if I found beta 1 here was positive, right? So that as police expenditures are higher, so if I spend more on my police force, I think the units that I had here was like $1 more per person. So if I spent $1 more per person on my police force, that's actually increasing crime rates. Well, that seems kind of weird. If I spend more money on my policing, you think crime rates would go down. But I've only controlled for unemployment here. There's probably a myriad of other things that help me predict crime rates. And who are the counties that are spending more on their police force? Probably the ones that have a lot of these other issues that are resulting in higher crime. So of course the counties or the states that are spending more on their police force are probably having higher crime rates, because we haven't controlled for all those other reasons why they might be spending more on their police force, right? I controlled for one of them, that unemployment was higher, and maybe the average income in the area is lower, and maybe there's fewer job opportunities, but I haven't controlled for all those other things. I've only controlled for just unemployment. Another way to think about this is, let's say I ran that regression of birth weight, and I had the mother smoking variable on the right-hand side. I'll guarantee you, every time you run this regression, it doesn't matter what sample data you have, you're going to find a negative coefficient on mothers smoking while pregnant on birth weight. However, I didn't include any other control variables. So what do you think is probably true? Like, what's something that might be impacting birth weights that would be correlated with being more likely to smoke while pregnant? Well, if we had any measure of like what income status or what the socioeconomic class of the individual was, individuals with like lower income are more likely to smoke while pregnant, or they're, people in lower income class less likely to be able to get to higher levels of education. Higher levels of education make it less likely you smoke. So, there's these things that we're not capturing that are probably driving a large amount of this effect. I am not saying smoking while pregnant is going to end up being positive or have a good effect on birth weights, but it's likely that if you just run this simple linear regression, you're picking up not only the impacts of smoking while pregnant, but the impacts of being in a lower income class, having lower levels of education, right? Especially if you have lower income, you can't buy as high quality foods, you don't have access to the same prenatal care. And so you're picking up all those negative effects as well here. Now, if we can control for those, we'll see that this is still negative, but it becomes smaller, right? It doesn't have as much of an influence. So we need to be cautious when we haven't controlled for a lot of other things, because those omitted variables could be playing a large role. So the other one, I always like this little graphic. If we had, annual numbers on autism rates and organic food sales, we would find a huge impact of organic food sales on autism. Organic food sales aren't changing autism rates, right? It's that there's probably something correlated with both of these that's driving both of them, right? So if individuals are, in the US are having an increased, what am I thinking about here? Like an increased focus on health, right? Then more kids are going to be going to the doctor. We're going to be investigating, things a little bit more. It's more likely we can pick up autism. And also we care more about our health. So people are more likely to be buying organic food or, going vegetarian, whatever it is. And so it's a third factor that's driving both these things. But if we didn't include it into our regression equation, it's going to look like organic food sales are causing autism rates to go up, which, intuitively we know is probably not real, right? So we need to control for these other factors. We can't simply just look at that coefficient, because, it's evidence that there's correlation, not causation, right? And it's likely because organic food sales are correlated with a lot of other things that are driving up autism rates. So the idea of correlation, not causation is, potentially we've got these variables X and Y. Now, one thing that could go wrong, not just with causation, but maybe we've got it flipped, right? Maybe we think that autism rates were being driven by organic food sales. So we had our Y variable as autism rates, but maybe it was that organic food sales are higher because people are having autism at higher rates, and maybe organic food is, something that can help, maybe the parents are more likely to buy organic foods. So we don't know which direction that relationship goes. Or it could be that we had these two variables, X and Y, Z is causing both of them, but Z is not in the regression, right? So it's going to look like these two things are highly correlated, which they are, but it's not that one of them is causing the other. It's that this outside factor, this other variable Z, is causing both of them, and we don't have that in our data set or as part of the equation. So this is always a good little depiction. So I used to think correlation implied causation. Then I took a statistics class, and now I don't, right? Well, it sounds like the class helped. Well, maybe, right? So maybe it wasn't taking the class that led them to understanding this. It was some other factor that made them more likely to understand it and more likely to take a statistics class, right? This outside thing that's causing both of them. So, and here's like a really formal slide of what's happening when we don't include important variables. But really, you could go through all this and just get to the bottom, which is, if I have these other variables, call it X2, that matters, and I don't include it in my regression. So this X2 is before I was calling it variable Z, right? That the estimate that you get for the relationship between whatever X variable you included in the regression and the Y variable will pick up the true relationship, but also this additional factor, right? And so, if we had more time, or this was a more advanced class, we'd probably really dive into thinking about how we can determine what direction the bias is going to be. But really all we need to know is that if we have important omitted variables, we're going to get predictions that capture not only the true effect, but the effects of the variables that we left out as well. Okay. So we kind of already went through this example. I kind of jumped the gun a little bit, but I want to show you a few more things in Excel. So, oops, I didn't mean to hit escape. Or I didn't mean to hit it. So if we go back, let's look at this GPA data again. Okay. So I'll show you a few things as we're working through this. What was I going to do? Oh, so let's think about looking at that output where we had every single variable included. Okay. So I want to point out one variable specifically because sometimes the interpretation gets a little tricky. Okay. So let's look at this high school rank variable. Okay. It has a negative coefficient associated with it. So what that's saying is if we think about high school rank, what's the best ranking to be? Number 1. So this is kind of a weird variable in that when I see a 1 unit increase, it's actually someone moving down their class ranking, right? So here, a 1 unit increase would like be going from a 1 to a 2, being top in your class to being second in your class. So if I go from being first to second in my class, my predicted GPA in college would be about 0.003 points lower, which makes sense, right? Because as I'm moving up the ranking, I'm actually moving like down their GPA, their high school GPA. So sometimes if you have a variable like that, it's kind of a weird interpretation because a 1 unit increase isn't actually someone getting better, like moving up the rank, it's actually moving down, right? So sometimes these variables will be a little bit tricky with their interpretation. Yep.
And how does Excel know how to do that?
So,
That is so confusing.
all right, so we'll go back, and I think I can give you an idea.
Like how do they know the ranking is even important and know it's going down one?
How does Excel know? Okay, so remember when we just had one variable on the right-hand side?
Mm-hmm.
I said if we took a derivative in respect to those two things, set them equal, we can come up with these equations. We can basically do the same thing when we have all of these. It's just going to be this equation is going to have a lot more going on. Jeez. So they're going to have a lot more going on. It's going to be there's still a way you could do, you could still do the intermediate steps in Excel if you really wanted to when you have multiple variables, but it's just going to be a mess. It does it for you. So that's how it knows the equation. So once it has that equation that factors not just one X variable, but multiple X variables, right? It runs that equation using the actual data, right? So when it looks at high school rank, Excel doesn't know that your GPAs are going to go down if you're ranked lower in your class or higher in your class, have a higher number, but it does have the actual values. And so it just picks up what the correlation is. So it's just picking up the correlation that when it's going through this variable, when it sees high school rankings that are lower, it's picking up that the GPAs are also low. This is hard to say because when I say rankings lower, I mean that you're falling in your class. Yeah, yep. Does that make a little more sense? I mean, so it is crazy that it can do it that fast. And if you really think about, especially here we've got 4,000 observations. You can use, Excel is limited, but you've got these other statistical programs. I think I had a data set the other day, I was looking at NBA shots, and it was something like 1.4 million observations. And it can do the same thing that Excel is doing here and spit out at you coefficients like it's nothing, which is, yeah, I am bewildered by it all the time as well. I don't understand how we've got to the computing power we did, but I'm glad we're there. So, it's really picking up all these things from it's coming from data. Just like our sample mean came from data, these coefficient estimates are coming from actual data points, right? Yeah. Sorry, hopefully I wasn't geeking out too much about it because I like this. This is my favorite part of the class, because this is the stuff that's the most useful, right? If I can understand relationships between things, I can start to make predictions, right? And I can start to, so speaking of predictions, if we go to that, let's actually go to an easier one just because we don't have as many moving parts. So let's say I just look at the regression where I had athlete and SAT scores. What I can then start to do is come up with my predicted Y values. So let's say I want to come up with, I'll write a predicted GPA, or kind of think about this as GPA hat, right? I would come up with this prediction for the Y variable. And let's say I tell you that this person is a student athlete and has SAT score of 1,200 we'll use, right? So as long as once I obtain these coefficient estimates for any person, I can predict what their GPA would be. How would I do that? Well, they are a student athlete, so I would take a 1 there, multiply it by the student athlete coefficient. I then say, okay, now take the coefficient on the SAT score, and that's the effect of 1 unit. Well, this person scored a 1,200, so I need to know the impact of 1,200 points. So I just multiply that coefficient by the person's actual SAT score. Now I come up with a predicted GPA. And I could play around this, right? Maybe I don't want to do 1200. Maybe I want to look at someone with a 1400, right? And then I kind of come up with that prediction, right? So I could do this for any combinations. So that's, once we have these coefficients, we can come up with these predictions for, any person, even if they weren't in the data set, right? Well, then it starts to get really wild, right? What if I've got all of this information? Okay, well, for right now, for the sake of being able to see things, I'm deleting these. These are confidence intervals that we don't really need. We're not going to use them for anything in this class. So I'm going to say, let's come up with a prediction for a hypothetical person. This is the easiest way to do it on that fifth Excel assignment, but also just in practice. Probably the easiest way to do that. Actually, I'll probably move this down one. So let's say that I've got an individual and I start to give you a bunch of information on them. They're a student athlete, they're male, they took 40 credit hours, all this stuff. So I'll just start walking through this. So I've got a person who, let's say, is not a student athlete. So I'll put a 0 in there. Their SAT was an 1150. Oops. 1150. Oh, what? I bumped a button. There we go. I don't know. Let's say they were, 12th in their class. Their verbal math score, and I always forget what the range on this was. I think it was 0 to 100. So we'll just say they got like a 70 on it. Let's say they are female. They're white, which makes the black variable 0. Total credit hours, let's say this GPA is based off of they have 75 total current credit hours. And their high school size, I forget, this one is measured kind of weird. So it looks like it's range. Let's say, I don't know. I think this represents like thousands. So let's say it was 2.68. So that would be 2,680 kids. So 2.68. And I won't give you a variable like this high school size where I kind of alter the units. I would probably keep it as in the thousands so it'd make a little more sense. But I basically just write down what the values for each of these variables would be for this hypothetical person. I then go through and say, well, really, what am I trying to do? If I'm trying to come up with a predicted GPA, think about it this way. So I'm trying to predict GPA, not plus, equals. So I will take whatever the intercept value is. I'll then add to that whatever the first coefficient is times that person's hypothetical value for, say, are they a student athlete? Then add to that, I don't know why I'm writing on an angle here, the coefficient on SAT score, etc., all the way out, right? So basically, I'm just going to take every coefficient estimate, multiply it by the value for that hypothetical person for that variable. And then at the very end, I need to not forget, add in the intercept, right? So I've got everything lined up here pretty nice so that I can just do this. Take the coefficient for that athlete variable, multiply by whether or not the person's a student athlete. I'm then going to copy this down and just do that for every single variable, right? Because that's what I want to do. I want to take the coefficient and multiply it by the value of that variable for this person. Once I have that, I can add all these up. Now, I forgot the intercept here. So eventually I'm going to have the intercept over here. So I'm going to select all that and I get my predicted GPA. Now, one of the problems is, right, I need to add in my intercept. So I'm going to put that up there. I actually think I screwed up this verbal math score. I think maybe it was on a much different scale. Let's see. Yeah, I think it was not on a 0 to 100 scale. So I forget. Let me see the raw data. Oh, this is between like 0 and 2. So yeah, I really had that screwed up. So let's say their verbal math score was a 1.5. I don't know the scale on which this test was measured, but it was some test that the college that put out this data had. So now we start to get a prediction that makes a little more sense. So if you put in the wrong value, for these variables, you will get something kind of weird, but that's because you should only be putting in hypothetically like real values. So, someone who, lists all these attributes, right, we would predict they would have a GPA of about 3.07. So this really kind of starts to show the power of obtaining these coefficient estimates. You can make predictions for people And this person could have even been someone who wasn't even in the data set. Any questions on anything I just did there? I know I kind of did it a little bit quick, but you know, as long as you have it set up like this, where you're entering in that person's values like right next to the coefficients, makes this a lot easier. The other thing that you might be asked to do is something like, let's say I wanted to know which of these variables can I say have a significant relationship with GPA at the 1% significance level. So my alpha will be 0.01. So I might want to go through, I want this to be able to give me another column. Here we go. So maybe I want to come up with rejection decisions. I don't know what button I accidentally keep hitting that's doing this, but, right? So I look at each one of these variables, and at the significance level of 1%, so alpha is 0.01, this is where I have to be careful. When I see these e to the negatives, that's a p-value of pretty much 0. So would I reject here? Yes, I could. So I put in the word reject, and I could go through and do each one of these. What's something else I could do? If I'm worried about looking at these wrong and saying, well, look, I thought this one I failed to reject because I thought the p-value was 3.7. I forgot, you know, the p-values of probability can only be between 0 and 1. So I made some wrong decisions because I wasn't looking at these e to the negatives right. Well, let's just do what we've kind of done with the other hypothesis testing. Let's use an if statement. Just going to delete this. So if that p-value is less than, oh, what is going on here? Hold on. I think I'm, okay. I hit some button. I don't know what it was now. Okay, let's see if I can get this to work now. It's still not letting me type in here. What did I hit? Number lock maybe? I'll try closing these other files real quick. Sorry, this will be the last thing we'll do, so hopefully bear with me. There we go. So I could use that if statement, just like I did when I was doing other hypothesis testing. So if the p-value, is less than my alpha of 0.01, if that's true, put the word reject, comma, if it's not, put the word fail, for fail to reject. Well, now when I copy this down, it'll take the p-value of every single variable and tell me my rejection decision. Notice here, oh yeah, my p-value is 0.1, I should fail to reject. Oh yeah, p-value is 0.8, I should fail. All these other ones, right, these e to the negatives, those are all pretty much p-values of 0, so that's why I'm rejecting all of those. So I can say that the only variables here that don't have a significant relationship with GPAs is this verbal math test. So if I'm advising this college, I tell them, stop wasting money on giving this test. It is not a good predictor of GPA. It's a garbage test. It doesn't tell us anything about their actual ability. I also say, well, look, looks like kind of racial things aren't really playing a factor here as well, right? It looks like there's not much of a correlation between kind of being white and GPAs here. So, we can do that pretty quickly using that if statement. Otherwise, you can go through each one of these by hand and compare them to the alpha. But, if you're doing this in Excel, you might as well kind of use the tools of Excel to make it a little bit easier for you. Because it is really easy to sometimes look at these, like especially if you've got, so all of these make a little more sense, but like let's say I had if it was showing me 0.2 times e to the negative, well, then I might look at that and think that I can reject at certain things, even though it's basically a p-value of 0. So setting up the if statement makes me, a little bit less likely to accidentally make that mistake. Any other questions from me? Check the chat. Okay. So this is about as far as I would expect you to kind of do stuff in Excel. So being able to run these regressions, thinking about how to make predictions, how to interpret these coefficients and the intercept coefficient, how to make rejection decisions is really kind of all I'm going to be kind of expecting you to do. Right? Now, hopefully the more examples we work through, and I'll go through some more examples on Tuesday, the more interpretations that we see, the more times we think about, oh yeah, the test statistic is just the coefficient divided by the standard error. Oh yeah, the p-value, I make rejection decisions the same way I was doing with other hypothesis testing. The predictions part is probably the hardest part to understand, so I'll make sure I do another example looking at that on Tuesday as well, kind of bringing in some additional data sets, but I'll save this, and post what we did today up on Canvas. So let me label that just in case someone's kind of looking at it after the fact. Okay. So I'll save this, and I'll when I post this, I'll probably label these sheets a little bit differently as well, like, you know, kitchen sink, only athlete, whatever, athlete and SAT. So you'll have all this to look at. So we kind of talked through, yeah, we got through every slide. I think we should be kind of right where I want to be. I don't want to do an online quiz, but I want to know what types of examples you guys want to see next week, because I've got data sets on a myriad of different things. So I'll probably put up a graded survey. So like you just have to get on and do it, but it still is going to be worth like the 10 points like an online quiz would be. And basically just ask you what topics you're interested in seeing me work through some examples on. Because I have data on a lot of different things. And there's quite a few I can think that would be of interest, but I want to make sure that it's of interest to the majority of the class. So I'll get that kind of posted once I get back to my office, have that submitted before we meet in class. Well, I can't bring those examples on Tuesday. Let's do it this way. Instead of doing an online quiz today, if you have things that you're interested in, and I realize I'm not going to get a flood of emails off this, but if you want to just shoot me an email and say, I'm interested in this, I'll try to find some data to bring in on Tuesday for it. So that way, I guess people who are motivated enough to send me an email that want to see examples through whatever they're interested in, they'll be more likely to actually see that example work through. Okay. Any other questions for me? All right, so we'll keep on continuing. No like real new material next week, just more linear regression stuff on Tuesday, just more examples, and then starting some exam review Tuesday, carrying that into next Thursday. I will be doing an exam review, and I'll get an announcement of this in my other sections that Monday of exam week, because technically it's like the last day of class. So I'll post the hours where I'll be doing those reviews, and I should be able to make the Zoom link available to you as well. So if you want to watch it live, you can. If you don't, I'll be posting those on YouTube Monday as soon as they're over. So you'll have some additional practice materials there as well. Okay. All right. I will see you guys. Oops. Stop the video. I'll see you guys on Tuesday.
I was going to ask the Connect. So if we finish all the Connects in Excel, was